All right, well, in Investigation 3.2, we start covering more here of inverse variation. And our focus question is, what examples using distance, rate, and time show one variable inversely related to another? So in our little story here, it says the relationship between length and width for rectangles with a fixed area is not linear. Remember in 3.1 we did that investigation. We proved that it wasn't a linear function because it doesn't increase by a constant rate of change. As L increases, W decreases, but not at a constant rate. The graph is a curve showing how L and W relate to each other. The relationship between L and W is an example of an important relationship that we call inverse variation. And they show you two equations here. The two non-zero variables are y and x and y are related by an inverse variation if, and again, x and y meaning they're not zero. They can't be zero. So you get y equals k over x. You can even also use x equals k over y. Either one, or x times y equals k. Just like we worked about. Again, where k is a constant other than 0. That's our number that always stays the same. So some other questions that we're going to look at as we get going here. How does the value of one variable change at the other variable, at the value of the other changes? How is the pattern of change shown in the table and the graph? And then what are the equations? We're going to go all over that in our first example here on the next page, example A. So we're going to do one together, and then we're going to have you guys work one. We'll put it all together here. So it says inverse variation occurs in many situations. You probably thought about how the length of a trip depends upon the speed. So it says Mr. Cordova lives in Detroit, Michigan. He often travels to Baltimore, Maryland to visit his grandfather. The trip is about 500 miles away, and here are the notes that he took over his last year to Baltimore. So the different travel times. Now again, if we're trying to find a constant, if it's inverse variation, the constant's going to be this number right here, 500, right? So that never changes as distance. The speed travels because, or the time travel changes because he goes by plane for 1.5 hours. He drove 10 hours. He drove and had to stop 14 hours. He flew 4 hours. Flight got delayed, and he took a train 18 hours. So all those are different means of travel. So if we take our travel time, okay, and talk about that distance traveled, right? Because that's what we're looking to relate it to. All right. So if our travel time on the first one, travel by plane, was 1.5 hours, all right. So on my calculator, if I take 500 and divide it by 1.5, all right, I get 333.3 repeating. That was our average speed. And that sounds about right. Planes go very fast. That's why they have to be able to fly. All right, if we go ahead and do our second one, which took 10 hours, if I divide 500 by 10, I get 50. And again, that sounds about right, driving 50 miles an hour, so gets there in 10 hours. The next one now, it took him 14 hours, so his average speed obviously goes down a little further to 35.7. All right, the next one he flew, that was 4 hours. Okay, and it's 125. And then the last one took him 18 hours. And if I take 500 divided by 18, is 27.7 repeating. Okay, so there's our 5 values. So if I go ahead and graph those 5 values down here, all right, so if this down here is time travel, and this over here is our average speed, So we will go ahead here. Let's pause this for a minute here. Alright, and now we're going to fill in our bottom here. And we'll go by 2 so we can fit everything in. Alright, so now it's just plotting our points. So, lost it here. Alright, so our first point was 1.5, which is halfway. This is 0, 1's halfway, so a little bit more. So if this is 1, and halfway of halfway, we're going to go up to 333.3, so roughly about there. Then our next one was at 10.50, right there. And then 14.35.7. It's a little down, so again, the best you can do is estimate there. 125. That's halfway. And 18.27, which is just a little higher than halfway. So if you see our points there, I'm going to take a second to pause and orient this board. Alright, so if I try to connect my lines here, you can see that we have our curve. And this is not linear. Alright. Can't keep it like this. This board is out of whack. Alright, so it says write an equation. Well, again, remember, the equation for, if we use speed and time, remember they gave us 3 equations on that first page, right? X, y equals k, y equals k over x, and x equals k over y. Those are the 3 general equations of inverse variation. So if I'm going to replace x and y with s and t for time and speed, well, I know the first one is speed times the time travel equals, and what was our distance? 500. That's how many miles we traveled. So that's one possibility. And speed could equal 500 miles over t as one of the variables. And I can simply do that by taking the first equation and dividing both sides by t. That's how it transforms. So all these equations are the same. Or I could have t equals 500 over s. All right. So those are our 3. And there's a relationship between time, distance and time, and inverse variation. Explain why. So this is how we're going to explain it. The relationship varies inversely because s times t equals 500 for every value. And the graph shows that as time travel increases, average speed decreases. Also, our table doesn't show a shows a non-constant rate of change. Okay, So that's how we can find inverse variation. So if you go to the next page in part B, okay, it's a very similar question, but I want you to pause the video and I want you to try to do part B with your group. Okay, so your scenario is the Cordova family is planning a trip of 300 miles to Mackinac Island near the Upper Peninsula of Michigan. Mr. Cordova does the same calculations to see how the time travel will change if the family drives at different speeds. So again, they got different speeds posted here with different times. And just kind of like we did in the first one, I want you to go and see if you can go ahead and answer 1, 2, 3, and 4. We're going to give you about 10 minutes to do this. So if you pause the video, we'll see how you did. Okay, now that you've had time to solve the problem and use the example A as a guide, they wanted to describe the change as time travel, in time travel as the average speed increases. Well, if you look here, time travel is doing what as we look down the line here? Right, this is decreasing, right? And if you look at the speed, what's happening to the speed? It's increasing. So again, as average speed increases, travel time decreases. And again, this is the most important thing, at a non-constant rate of change, because that's telling everybody right now it's not linear. Okay. So again, what equation relates time travel to average speed? Well, again, what was the constant here? The constant here was 300 miles. So you could have had S times T equals 300. You could have S equals 300 over T, or T equals 300 over S. All the same equation. Okay. So if we go to graph what you did, okay, if average speed is down here, and we increase by 10, so we're just going to do that on our graph. And for the time travel, the biggest number we have is 10. I think this guy goes up to 10, so why don't we just go, we'll go by ones. Let's go up a little bit here. All right, so this is travel time. That's in hours. And average speed is in miles per hour. All right, so we have at 10, we have the average speed at 10 hours is 30. So there's a dot right there. And then at 40, the travel time is 7.5, so halfway. At 50, it's 6, right here. 60 is 5. And 70 is 4.3, so just above 4, maybe on the lower side, just below the half. So you can kind of see here that this graph has a very slight curve, but a curve nonetheless. Okay. So to answer the question down here for number 4, is the relationship between travel time and speed and inverse variation. Why or not? Why not? Well, again, it is inverse. And it's inverse because as your average speed increases, your travel time decreases at a non-constant rate of change. It's basically what we answered there in question 1 of this story. That's our answer. It decreases at a non-constant rate of change. the graph has a curve. All those things point out to inverse variation. All right, getting ready to wrap this up here on the very back page, part C. Taking this to one last level here. So it says, suppose Mr. Cordova decides to aim for an average speed of 50 miles an hour for a trip to Mackinac Island, which means his speed does not change. So again, if we start off here at 0, 0, and however many hours it takes to get there from wherever he's at, right? 1, 2, 3, 4, 5, 6, and he's going to keep everything at 50. So that's what our table should look like. Because if you multiply travel time times the distance, miles per hour, you're getting, I'm sorry, if you divide miles by time, 50 divided by 1, 100 divided by 2, you're getting 50 every time. So that's your constant rate of change here is 50. Alright, so if we go to graph this, so we got distance and travel time. And our travel time was this, 0, 1, 2, 3, 4, 5, 6, 7. And we'll just go up here by 50s. So obviously if we don't go anywhere, we don't go any speed, and then we're here. And you should notice something. So again, if you describe this pattern of change in distance as the time passes, well, as travel time increases, what happens to the distance? The distance is going up, right? The distance increases. And the distance increases at a constant rate of change. Because we have a straight line. So if I'm going to make an equation relating that distance to travel time, all right? So if our distance traveled is going to equal 50 miles per hour, so that's 50 times t, and basically the y-intercept here is 0, right? So when it asks us number 4, is this an inverse variation or not? No, it's not an inverse variation. What function is it? Right, it's a linear function. It's a linear function because this graph increases at a constant rate of change. So because this is a straight line and increases at a constant rate of change, it's not an inverse, it's linear. All right, so on the back of this packet is your homework assignment. You can use these examples to help you. And we're going to stop the video. Put it on